right. Hi, I'm Abhishek from LinkedIn. Today, along with my colleagues, Salil and Nizar, I'll be talking about Hodor, which is a framework that we've developed at LinkedIn to detect and address microservice overload. Many engineers have contributed to this project, so the three of us are here presenting on behalf of a much larger group. Before we get started, we would also like to thank JCON for allowing us to share our work in this forum. Just as a quick note, please hold on to your questions till the end of the presentation. I promise that we've left enough time for questions and answers. Next slide, please. Hodor, as it reads here, stands for Holistic Overload Detection and Overload Remediation. As was the case for the beloved fictional character, Hodor's job is to sense danger and protect against that danger. In this case, the danger of overloads to microservices. To give you an idea of the scope of this project and its success, Hodor has been in production for over a year and has been rolled out to thousands of LinkedIn microservices. Next slide, please. This is the agenda for our talk today. I'll start off by discussing the problem of overloads. Following this, Salil will talk to you about the various overload detectors that we have in production at LinkedIn. And he will also go over some examples of success stories where these overload detectors caught overloads in production. Nizar will then discuss how Hodor responds to these overload detectors to pull the system out of overload and into a safe state. Finally, we'll wrap things up with some miscellaneous remarks. Next slide, please. All right, so what is an overload? An overload happens when a resource is being asked to do more work than it is capable of handling. An office worker being asked to do more work than they have time for is an example of an overload. Similarly, in the distributed systems context, a server or set of servers being asked to process more traffic than they have been designed to handle is also an example of overloads. Servers can either get overloaded because of physical resource limitations or virtual resource limits. Next slide, please. Examples of physical resource limitations include CPU, memory, disk I/O, and network bandwidth. For example, if you have 24 logical cores on a system, you have 24 CPU seconds per second to do useful work. This limitation is a function of the number of cores. You can add CPU cores to get more CPU time, or you can change the characteristics of the existing cores to do more work in the same amount of time. The bottom line is there is a physical bottleneck. And once a workload or set of workloads exhausts the CPU resource, the system will hit an overload. We can follow a similar thought process as I just laid out for CPU to think about other physical resources. For instance, in case of memory, there is a finite amount of memory, which is a hardware characteristic. Similarly, storage devices, whether spinning disks or SSDs, are rated for IOPS, which is also a finite resource based on hardware characteristics. Any of these resources being exhausted because of an excessive workload will cause the system to enter overload, resulting in degraded performance. Next slide, please. All right, so now that we've talked a little bit about the physical resources, let's look into what virtual resources are. Now, virtual limits or virtual resources are different altogether, but they can have a very similar impact when exhausted. Some examples of virtual resources include threads available for execution, pooled database connections, or semaphore permits. These resource limitations are often created by software engineers as a result of certain design paradigms. For example, a software engineer might choose to create a thread pool with 100 threads. In such a case, there is a virtual limitation on the number of synchronous requests that can be processed concurrently. Next slide, please. Now let's look at some overload scenarios that we have observed in production at LinkedIn. Next slide. All right, so the first overload scenario that we observe really most frequently at LinkedIn is because of an increase in traffic. As shown in the diagram on this slide, a server is perfectly capable of serving a certain amount of traffic with acceptable latency and throughput. But as the traffic to the server increases, we typically start hitting physical limitations such as CPU constraints. This causes the performance to degrade very rapidly. In such scenarios, it's only a matter of time before the server falls over. Note that this increase in traffic could be because of more traffic organically because of more clients or because of fewer servers. Next slide, please. The second overload scenario that we observe pretty frequently as well at LinkedIn is back pressure from downstreams. In such scenarios, a downstream service might become slow to respond, resulting in requests piling up at the upstream. This is known as back pressure. In our services, we typically find that this results in virtual resource overload before a physical resource limitation is hit. Next slide, please. The last and most tricky overload scenario that we encounter is a result of noisy neighbors. In any sort of a microservice cloud deployment, whether VM or containerized, applications are constantly being co-located on the same physical resource. This creates a risk that a service might get co-located with an abusive neighbor, which in turn will affect the performance of the service in question. In the top diagram, you see how two well-behaved co-located neighbors are able to serve traffic. Both neighbors, the server as well as the neighbor, are able to deliver their slated performance. In the bottom diagram, you see noisy neighbor stealing resources and resulting in overloading the service it is co-located with. Such scenarios can be the trickiest to identify because they are completely random and unpredictable. Next slide, please. Now, we've discussed some of the examples and scenarios of overloads, but the question remains, why are they so important to us? It's because if left unchecked, overloads can be devastating. They can result in cascading failures capable of bringing down an entire site or service. Next slide, please. All right, so now that we understand the different types of overloads and associated risks, let's talk about the goals of Hodor as they pertain to overloads. The first goal of Hodor is to detect different types of physical and virtual overloads in real time with minimal overhead. This is important because Hodor runs on all services at all times, with the goal of improving performance and availability. So any overhead because of Hodor is highly undesirable, not to mention ironic. The second goal of Hodor is to take evasive action to mitigate these overloads to improve service resilience and availability. Currently, this evasive action includes load shedding. The third goal is to provide an out-of-box solution that works for all LinkedIn services without service owners or SREs needing to tune the algorithm. And lastly, the most important goal here is to have a neutral to positive member impact. Everything that we do is to improve our member experience, and a solution that would result in a net worse member experience is unacceptable. With that, I will hand it over to Salil to talk about the various overload detectors that we've built.
Thanks, Abhishek. Hi, everyone. My name is Salil. I'm a staff software engineer at LinkedIn. So now that we are familiar with the goals of Hodor, let's deep dive about how we accomplish this goal of detecting different types of overload. In this section, we'll take a deeper look into different types of overload detectors that we've built as part of Hodor. Now we'll be looking at 4 different types of overload detectors. The first two detect an overload of a physical resource, CPU and memory. The third one is for detecting overload of a virtual resource. We'll be focusing on a thread pool detector today. And the last one is an additional confirmation filter that we have added to prevent false positive firings of overload detectors. Now, before I jump into the actual individual detector design, I want to clearly call out one thing. It is extremely important for our detectors to have high precision. In other words, the detectors should not fire an overload when there is no legitimate overload. This is because the price that a service has to pay when one of our detectors fire is very high. As Abhishek mentioned, the action is load shedding. And therefore, the main guiding principle that we have followed when designing all of our overload detectors is to make sure that we prioritize precision over recall. That to make sure that all overload firings are true positive firings of an overload. Now, the first overload detector that we'll look into is CPU overload detector. The objective of CPU detector is to quickly and accurately detect CPU overloads in real time with minimal overhead. Now, the main idea here is to have a simple, lightweight background thread, which is running at the same priority as all other application threads which are executing your business logic. This background thread is known as the heartbeat thread, and hence the name heartbeat overload detector. The heartbeat thread is scheduled to wake up every few milliseconds. Just as an example, let's say 10 milliseconds. Now I want to point out that the overall amount of work done by the heartbeat thread is very trivial. And we have ensured that it adds no measurable impact to application performance. The heartbeat overload detection algorithm monitors whether the heartbeat thread is able to get CPU every 10 milliseconds. Once the algorithm realizes that the heartbeat thread is consistently not getting a CPU core to run on at the expected time intervals, we flag an overload. Now, it is important to note here that just a few variations are not enough to flag an overload, and that the algorithm will flag an overload only when we have high confidence that the CPU is indeed overloaded. Now, as Abhishek mentioned, Hodor aims to have an out-of-the-box solution that works for thousands of microservices at LinkedIn. These microservices have widely varying characteristics. And hence, coming up with the appropriate variables and parameters to make sure that maximum precision is observed for all of these varying types of services is a challenging task. To provide a concrete example, we may have the heartbeat thread sleep for 10 milliseconds each time. And let's say in a window of 1 second, if the 99th percentile is worth, let's say, over 30 milliseconds, then we say that this window is in violation. If let's say 10 consecutive windows are in violation, the service is considered overloaded. As I mentioned, the values for these thresholds and for these parameters are determined by doing extensive synthetic experiments, as well as sourcing data from production services and comparing it with performance metrics when the services were considered to be overloaded. And lastly, the rationale behind using this approach of a background heartbeat thread is that one, it directly measures the useful CPU time available to the application in real time. So what I mean by that is something like a top command might say you have 30% free CPU available. However, that might not necessarily mean that your application has that CPU available in real time. And secondly, the concept of heartbeat thread is simple and applicable everywhere, irrespective of the environment or application type. This is an example of the heartbeat CPU detector in action. In the top left graph, you can observe that the heartbeat detector is able to capture a CPU overload, as can be evidenced by the bottom right graph, where the container 95th percentile CPU usage is spiking considerably. To correlate this with business impact, other KPIs such as average latency and P90 latencies have been spiking more than 2.5x. So this is an example of heartbeat detector catching an overload in production. Now let's move on to the next detector, which focuses on memory bottlenecks. Now the objective of GC overload detector, similar to heartbeat, is to quickly and accurately detect increased garbage collection activity for applications with auto memory management. Now the idea here is to observe overhead of GC activity in a lightweight manner. Deep diving a little bit more, on each GC event, we calculate the amortized percentage of time spent in GC over a given time window. And we call this metric as a GC overhead. A schedule is then set up on top of this GC overhead. Additionally, the GC overhead percentage is divided into multiple tiers. And if the duration spent in GC exceeds the violation period for that particular tier, we fire an overload. Now, of course, as you can imagine, the violation period is smaller for higher GC overhead tiers, as higher GC overhead tier indicates more severe GC activity. For example, a GC overhead of 10% or more consecutively observed for 5 seconds plus would be enough to flag an overload. Now, the rationale behind using the percentage time in GC is that it uses both GC duration and GC frequency that can catch different types of GC issues. And finally, similar to heartbeat thread, we came up with values for these parameters and thresholds that are applicable to all services at LinkedIn by doing extensive amount of synthetic experiments plus production experiments. Now, similar to heartbeat detector, this is an example of a GC overload detector in action. Now, in this particular situation, the GC activity had increased because of organic increase to the incoming traffic, which you can see in the left top right graph. Now, in the top left graph, you can observe that the GC detector is able to capture this and flag it as a GC overload. And similar to the heartbeat case, other KPIs or business impact indicators like the P90 and P99 latencies have been spiking considerably. Now that we have looked at a couple of physical resource overload detectors, we will take a look at a virtual resource overload detector. After extensive study of queue wait time, we came to the conclusion that there is a good correlation between increasing KPIs such as latencies and increasing thread queue wait times for synchronous services. For example, consider a synchronous service. Requests will start spending more time waiting in queue if current request processing time increases, right? Either due to an issue in the service itself or because there is an issue in one of its downstreams. The capacity of a service can also be reached when latencies of downstream traffic increases, which can have sort of a cascading effect where the number of concurrent requests being handled in the local upstream service will increase even though there is no change in the incoming traffic. However, with Hodor's thread pool detector, without knowing anything about the downstream services, we can ascertain with high confidence at the upstream that by monitoring thread pool queue wait time, that there is indeed a thread pool starvation, and we can drop traffic at the upstream to alleviate problem that the downstream is facing. At LinkedIn, we use the Jetty server-side framework extensively, and hence currently we focus on synchronous Jetty services as the first target of our thread pool detector. Now, similar to the previous two detectors, here is an example of thread pool detector in action. When there was an issue in the downstream process due to a database slowdown that resulted in request pileup at the upstream, because of which requests had started spending more time waiting in the Jetty thread pool queue to be picked up for processing. This can be seen in the top right graph. In the top left graph, you can see that the thread pool detector is able to capture and flag this as an overload. And similar to previous cases, other KPIs such as average, P99 have been spiking by more than 12x in this case. Now, as I mentioned previously, while designing all of these overload detectors, we value precision over recall. However, after Hodor was rolled out to all services in prod at LinkedIn, we found an interesting scenario that was affecting about 1 to 2% of services. For example, let's say a microservice is suboptimally tuned for its GC parameters, because of which when the organic traffic or the organic incoming traffic increases, let's say during a data center load test, this suboptimally tuned GC service might see a lot of frequent micro stop the world pauses. Now, these frequent micro stop the world pauses might impact our background heartbeat thread, resulting in essentially CPU starvation of the background thread. However, if there is no business impact, if, for example, KPIs such as average and P99 latencies are not impacted, then flagging an overload and shedding load in this case would not be the right thing to do. Now, of course, the one solution to this was to go back and improve the GC health of these services, make sure they're optimally tuned. And we found that doing that does indeed help in reducing these false positive firings. However, we realized that we need to be future-proof, and hence we have decided to build a confirmation filter that can work in conjunction with a system-wide overload signal. The KPI that we have used here is average latency. And one of the things that I want to point out here is that not every latency increase is an overload, right? But every physical resource overload will result in latency increase eventually. The algorithm that we have used is based on standard, moving average crossover approach, where we maintain two sliding windows of varying lengths and use a tuned multiplier on top. And similar to all of the previous detectors, we have done experiments to come up with a multiplier that works well with high precision for most of the services at LinkedIn. Now, here is an example of how the latency confirmation filter helped remove a false positive in prod. In the upper row, the leftmost graph, you see that the heartbeat overload has been firing. However, in the top middle graph, there is no business impact. The average latency is unaffected. Now, for this particular service, the issue was that the service had a suboptimally tuned GC, because of which there was CPU starvation seen by the heartbeat thread. However, as can be seen in the top right graph, the combined heartbeat plus confirmation filter did not fire. On similar note, if you look at the bottom three graphs, the bottom middle graph shows there was a business impact to average latency that was accompanied with the heartbeat overload firing as well. Now, this is what we would term as a true positive, in which case the combined heartbeat plus latency confirmation filter was able to capture it. With that, I will hand it over to Nizar to talk about how we recover from overloads.
Thank you, Salil. Hey, I'm Nizar. I work as a staff software engineer at LinkedIn. Like Salil mentioned, once Hodor detects an overload in the system, Hodor moves on to the remediation stage. In majority of the overload instances, an overload can be remediated by reducing the overall request load in the system. To reduce the overall request load, Hodor performs load shedding of requests before the request consumes any resources in the system. Let's look into some of the load shedding strategies we designed at LinkedIn. Our original load shedding strategy was based on adaptive percentage-based load shedding. This shedding strategy drops a percentage of incoming requests and adaptively control the drop percentage based on how the system responds to load shedding. As you can see in the graph here, the load shedder continued to increase the drop percentage if the system did not recover from the overload. When the request pattern is not spiky, the load shedder will be able to find the right amount of drop percentage to keep the system in non-overloaded state. This is the load shedder's equilibrium point. In the graph, the top flat area is the equilibrium point. Once the equilibrium point is reached, it tries to stay in that level for some time and then do traffic probe by reducing the drop percentage. If the system again gets into an overloaded state during the probe, it will goes back to the safe equilibrium point and exponentially back off from the next probe. If it did not get back into the overload state, it will continue to reduce the drop percentage until it reaches to zero, as shown here in the graph. During the testing of this shedder with various traffic patterns, we identified that percentage-based shedder does not perform well when the incoming traffic is not stable. The equilibrium drop percentage identified by the shedder quickly become outdated as soon as the traffic conditions changes. It ended up not dropping enough traffic when incoming QPS increases, and sometimes it ended up dropping too much traffic when the incoming QPS decreases. Now let's look into the next strategy we followed to mitigate from this limitation. Due to the issues we encountered with percentage-based load shedding strategy, we were looking for a metric that represents the load on the system irrespective of the incoming traffic pattern. We ended up choosing concurrency as our normalized load metric. Concurrency is the total in-flight request in the system. The concurrency-based load shedder works exactly like percentage-based load shedder. This shedding strategy adaptively ramps up and ramps down the allowed concurrency instead of the percentage to control the load in the system. Once the concurrency shedder finds out the equilibrium concurrency, all other requests beyond the equilibrium concurrency will be dropped. So if more traffic comes in, more requests will be dropped. If the spiky traffic suddenly goes away, no request will be dropped, as long as the concurrency did not reach the equilibrium point. The graphs shown here are from one of the A/B experiments we ran, where the red host was unprotected and the blue host had load shedding enabled. You can see that as the overall QPS increases, the protected host is forced to increase the number of requests that are dropped. You can also see that the overall tail latency is lower on the protected host. But there are a few spikes where the load shedder is probing to see if the concurrency limit can be increased. One thing we noticed is that concurrency-based load shedding doesn't work well with the traffic prioritization during load shedding. I'll get into the details of this when we talk about traffic tiering. Next, please. Hodor rejects requests before any business logic get executed, so they are very safe to retry on another healthy host. This reduces overall member impact, since the 503 response is returned quickly to the client, giving it time to retry the request on another healthy host. But we don't want to blindly retry all the requests that are dropped by Hodor, because if all hosts in a cluster are overloaded, then sending additional retry traffic to them can actually make the problem worse. it will result in retry storm as shown here. To prevent this, we have added functionality on the client and server side to be able to detect issues that are cluster-wide and prevent any retry storm. This is implemented by defining client-side and server-side budget and stop retrying when the budget exceeds. Now let's look into how we introduce traffic tiering to prioritize the request. Next slide, please. At LinkedIn, microservices receive requests from members who are active on our site and also from offline systems, which needs additional data from services. Obviously, the request from online members is more important than the request from offline jobs. So to prioritize dropping less priority requests first, we introduced traffic tiering, where every request in our call tree carry the priority associated with it, to be able to use it intelligently during load shedding. Traffic tiering at LinkedIn started with the 3 priority levels: optional, degradable, and non-degradable. All online traffic are categorized into non-degradable, and majority of the offline requests are categorized into optional. So whenever there is an overload, the traffic tiering load scheduler prioritize offline requests to drop first before the online request. Now let's look into the implementation details of traffic tiering at LinkedIn. Traffic tiering load scheduler leverage histogram to approximate the right tier cutoff for load shedding. We started with a concurrency histogram for various traffic tiers. But in practice, we realized that concurrency-based histogram do not work well as expected, as the request drop does not contribute anything meaningful to the concurrency histogram. Due to this limitation, we came up with a rate-based load shedding strategy and a corresponding rate-based histogram per tier. The rate-based strategy works exactly similar to the percentage and concurrency-based strategies described earlier, but using throughput as the load metric. This strategy receives feedback from concurrency scheduler to improve its ramping and deramping strategies more intelligently. Next, please. Due to the success of Hodor in saving multiple production issues at LinkedIn, like Salil and Abhishek mentioned before, there are widespread interest across LinkedIn to leverage the signals from Hodor. I'll go through some of the related and future work in this area. One of the frequent asks from Hodor is to leverage the overload signal for auto-scaling the fleet. Currently, app clusters at LinkedIn provisioned with 20% headroom for the spiky traffic. Budgeting for the spiky traffic can be avoided if the fleet can auto-scale based on the capacity signals. So instead of provisioning the capacity for the spiky traffic, Hodor overload signals can be leveraged to help auto-scale just when there are spikes. Also, capacity engineering team at LinkedIn leverage signal from Hodor for load testing. The load testing tool terminates the test the moment Hodor detects an overload. The results of such tests are used to right-size the category of each app clusters. Also, we are currently working on increasing the Hodor coverage for data services. This needs careful treatment, as each data system will have its own specifics on various aspects of the data. We are also looking to develop additional detectors in future that are targeted towards specifics of certain stacks. For example, Parsec is an asynchronous framework developed at LinkedIn, and we are looking to develop a detector to catch overload in Parsec task queue. A similar detector is also being planned for native event loop. With that, we completed our session here. Thank you everyone for listening. We can get into the Q&A session now. Thank you.